Alright, in this video we kind of complete up the first section of Chapter 8 by turning our attention to applications that involve 2x2 systems of equations. We've been practicing how to solve the systems. Here we're going to have to create the systems first by interpreting the story problem modeling equations. We'll be looking for two variables and two equations. So let's go ahead and get started with the first example. This is a classic example, a mixture problem. It says how many ounces of 20% and 35% saline solution should be mixed to produce 15 ounces of a 30% saline solution. Now notice here that the mixture, the percent of saline is in between these two. It's not exactly halfway in between, because if it was exactly halfway in between, then we would use equal amounts of the weaker and stronger solutions. So what I'm going to do here is I'm going to let X represent the amount of 20% saline solution, and I'm going to let Y represent the amount of 35% saline solution. And we know that the mixture, that we have 15 ounces of it, so I already have an equation. Because that's the amount of the two things that are being mixing, that means X plus Y has to add up to 15. So there's one equation. I need a second equation, and that's where the percents come into play. Because it's 20% of X amount, X ounces of this solution, then if I multiply the percent times the amount, I'll get how much pure saline or salt there is. So if I multiply 0.20% as a decimal, 0.20, well, if I can put a decimal point there, we got it, times the number of ounces, and then do the same thing with the stronger solution, 35% or 0.35 times the number of ounces of that solution. That's how much pure salt in the first, how much pure salt in the second. And if we combine those, add those two amounts together, we should get 30% of 15 ounces. So 0.30 times 15. Now, the top equation, it's pretty much ready to go. The bottom equation, it's in standard form, and you know, except for the decimals, I'm not crazy about that. So what I'm going to do is I'm going to multiply through by 100, because there's two decimal places. And by multiplying through both sides by 100, I'm going to get rid of those decimals. Because multiplying, of course, 0.20 times 100, that's 20x, 35y. And so 100 times 0.30 is 30, times 15 is 450. If you want to, you could divide through by 5 to make the numbers a little bit smaller. If I divide through by 5, I get 4x plus 7y is equal to 90. Now, this equation here and this equation here make up my system of equations. I'm going to take this equation, I'm going to use the elimination method, I am going to multiply to get rid of the x's by -4. Every term on both sides. I get -4x minus 4y equals -60. I solve by adding the sides. Remember, if A equals B and C equals D, then A plus C equals B plus D. I add equal amounts to equal sides, and I get 3y equals 30. Well, that's an easy one to solve. Divide by 3, I have y is 10. And of course, if I go back to here, x plus 10 equals 15. That would tell me that x is equal to 5. So that's how many ounces I need of the two kinds. That's why I went ahead and I'm still using my 5-step method. I read the problem carefully. I state my variable, or variables in this case. So it says how many ounces of each. So you would need, or there would need to be 5 ounces of 20% solution. Well, that's why it's right. 20% saline solution. And 10 ounces of 35% saline solution. Now, because this is a kind of a problem for the mixture, that with the decimals and all, you're kind of looking at it thinking, well, I'm not 100% sure this answer even makes sense. Well, it kind of makes sense, and I'll tell you why. Exactly halfway between 20 and 35 would be 27.5. So that would be equal amounts of the two things that we're mixing. But our mixture is 30, more than that. So we would need more of the stronger stuff than we would of the weaker stuff. And that's exactly what I have here. I have more of the stronger stuff than I do of the weaker stuff. So that kind of follows suit. Alright, the next example. A boat takes 3 hours to go 24 miles upstream against the current. It can go downstream with the current a distance of 48 miles in the same amount of time. You are to determine the speed of the boat in still water and the speed of the current. Okay, now, here's what I'm going to do. I'm going to, because I don't know the still water and I don't know the speed of the current, I'm going to let R be the rate of the boat in still water. And I'm also going to let C be the rate of the current. Okay, and you may have noticed I wrote over here, distance equals rate times time. Because the idea here is that if I can multiply the distance equals rate times time, we have something working for us, and that what's working for us is that they're in the same amount of time. They're different distances, but they're in the same amount of time. So if R is the rate in still water and C is the rate of the current, doesn't that mean that with the current you'd go R plus C because the current's pushing you along, and against the current you would go R minus C because the current's kind of stopping you or holding you back a little bit, slowing the boat. So I'm going to have to finish it up here, but in 3 hours I can go 24 miles upstream. So rate times time equals distance. So my rate here is R minus C upstream. This is downstream. This is upstream. So R minus C is my rate times my time is 3. So I'm going to write 3 times the quantity. I'm going upstream, R minus C, and I'm going to get 24 miles. Now if I choose to, I could divide both sides by 3, and I would get R minus C is equal to 8. Then downstream with the current, I can go 48 miles in the same time, which was 3 hours. So 48 miles in 3 hours, that would be 3 times quantity R plus C, because we're going downstream and the current's pushing us along, it's speeding us up, and we can go 48. So if I was to, again, divide by 3, I would get R plus C is equal to 16. So I'm going to put that underneath. R plus C is equal to 16. And I'm going to look at this as my system. Well, this one is definitely set up for the addition method because I've got the R's lined up, the C's lined up, the equal signs, the constants, and look, it's minus C and a plus C. So if I add just now, I don't even have to multiply through either one of the equations by a constant, I would get 2R is equal to 24, the C's would cancel. So if I divide by 2, I would get 12. So the rate in still water appears to be 12, and this is in miles per hour. So to find the current, let's say I just go right over to here, this would be 12 plus C is equal to 16, so C is 4. So the current is 4 miles an hour. So it says, determine the speed of the boat in still water and the speed of the current. The speed of the boat in still water is 12 miles per hour, don't forget your units, and the speed of the current is 4 miles per hour. Now again, you might look at it and say, well, they're just numbers. I don't know if that makes sense. Sure it does. Because if the current's pushing him along downstream, he's going 16 miles per hour. So in 3 hours, he can go 48 miles. If the current works against him upstream, he's going 8 miles an hour. 3 times 8 is 24 there as well. So that matches up kind of nicely. The last example has to do with profit and revenue and cost. And so what we're going to do is we're going to kind of follow through here, and again we're setting up our problem as we go. A storage company rents its units for $120 per month. The company has fixed monthly cost of $2,100 and variable costs such as things like service and air conditioning and such of $50 a unit. You know, fixed monthly cost, that might be rental or insurance or something like that. So when we are trying to find the cost, we're going to combine the fixed and the variable. But the variable is changing. And in this case, it's changing based on the units. So we have write a cost function representing the monthly cost, C of x. So C of x for x units. Well, it's $50 a unit, so the variable cost would be 50x. And then we would add on the 2,100 of the fixed cost, and that wasn't so bad. Write a revenue function representing the revenue R of x for when x units per month are rented. Well, it's $120 for every unit, so the revenue R of x would be 120x. Now these are kind of like your y's here. Y equals this, y equals that. This is cost, this is revenue. And determine the number of units that must be rented in a month for the company to break even. All right, the break even point when these two amounts are equal. So when these two y values are equal. So if I was to use substitution, I would get 120x is equal to 50x plus 2,100. We want to set the cost and the revenue equal to one another to find where it breaks even. And that's a fairly simple equation to solve. I will subtract 50x from both sides. We're running out of space here. Divide by 70. And I will get x equals 30. So it looks like if they have 30 units rented, they will bring enough money in to pay for all their costs and break even for the month. So the number of units that must be rented for the company to break even. To break even, the company must rent 30 units in the month. All right. Now those are not the only kinds of application problems that you can have. They're just some of the types that you see most common in some of the more classic problems of algebra.